Hey everyone, today we are looking at section 3.5, which is all about symmetry. So when we look at symmetry, we know that a figure has symmetry if there's a rigid motion that can map the figure back on top of itself. So there's two types of symmetry that we're going to look at. And the first type of symmetry is line symmetry, which is also sometimes called reflection symmetry. So if I can reflect a figure across a line so that it looks the same as it did when it started, then that is called line symmetry. And the line of reflection is the line of symmetry. So like if I look at this kind of moon here, if I reflect it over this line, this point's going to map onto this point, and this point's going to map onto this point, and they are all going to reline up so that the figure will look just like it did when it started. So if we take a look at these, I want to know which lines or which figure has lines of symmetry. Okay, so when I look at a rectangle, I can cut a rectangle in half vertically as well as horizontally. So I can fold it in half both of those directions, so that way we can map the rectangle onto itself. Okay. When you cannot use with a rectangle, you cannot use a diagonal. A diagonal is not a line of symmetry. Try taking your piece of paper and fold it corner to corner along the diagonal and see if you can get the points to line up, and you will not be able to do that. Okay? Isosceles trapezoid. Again, we basically want to cut the figure in half so that it looks the same on either side. And if we do that here, we can do it vertically, but we cannot do it horizontally. If I tried to do it horizontally, this point would map up to here, and that wouldn't be mapping onto itself. That wouldn't look the same. It would look upside down. Okay? A parallelogram has no lines of symmetry. Okay? I can show you this in class. But if you try to cut out a parallelogram, again, you can use your paper and just cut off some corners, not your notes paper, of course, but cut off some corners and see if you can fold along the diagonals. If I tried, now don't draw this on your paper because it doesn't work. If I try to draw this point here is going to reflect over here. It is not going to reflect onto this point. Same thing if I tried to fold it the other way. If I tried to fold it on this diagonal, okay, this point is going to reflect over here, not over here. So parallelograms do not have any lines of symmetry. Okay, our regular hexagon has quite a few lines of symmetry. Okay, a regular hexagon is going to have a line this way. So that's one line. Okay, I'm going to have a line matching that on all of the other ones. So this is line 2. This is line 3. Okay. And then we're going to look at, well, what happens? I can fold this in half this way. So that's line number 4. Then I also can do line number 5 and line number 6. So a hexagon actually has 6 lines. Okay, rectangle is 2 lines. Trapezoid is 1 line. All right, if you have any questions about that, make sure you write it down on your paper. So what I want you to do is go ahead and give this one a shot on your own. So go ahead and pause your video and then come back when you are finished. All right, let's go ahead and check our answers. For the first one, we can say that if we know we have a triangle that has only one line of symmetry, then the triangle must be isosceles, because in your isosceles triangles, these legs are the same length, so they can be reflected onto one another. And then this line is going to be the perpendicular bisector of the base of your triangle. If I had a scalene triangle, there'd be no way to make it reflect onto itself. And if I had an equilateral triangle, I would have 3 lines of reflection. So the only way to get 1 is to have an isosceles triangle. And for part B, does every non-straight angle have a line of symmetry? That answer is yes, because I can cut any angle in half. I can bisect any angle and it will fold on top of itself. All right, so hopefully that makes sense. Again, if you have any questions, please write them down. Okay, the other type of symmetry that we have is rotational symmetry. All right, if a figure can be rotated less than or equal to 180 degrees. So this piece right here, where we say less than or equal to 180 degrees, is really important, okay? Because if you think about it, everything has a rotation of 360 degrees because you turn it all the way back around. All right, so 180 degrees or less is what's going to give us a figure that actually has rotational symmetry. So that just means I can turn this figure here and map this point onto this point and have it look exactly the same as it did when we started. All right, point symmetry is what this type of symmetry is called when you have a rotation of 180. So it only maps around twice. And the order of symmetry is the number of times that a figure can be rotated around. So if I take a look at just a second and I look, oh, that did go. And I look at just this figure right here. All right, I can say, all right, when I'm looking at this, if I take this figure and I rotate it until here, now it looks the same as it does here. That was one rotation. Then I can go around 2, 3, and then 4 times we'll get this back to the beginning. So what I do is I'm going to look at saying, okay, the number of times I had to spin it. So if I start at this point, it goes 1, 2, 3, back around at 4 times. All right, so the order of symmetry for this little basically ninja star kind of looking thing is 4 to 4. Okay, the order of symmetry is 4. The angle of rotation, to find the angle of rotation, we do 360 divided by the order. Because 360 is a full circle, and the order of symmetry is the number of times it takes us to get back around. So let's take a look at how that works. Okay, we have a rectangle, and I want to know if I can spin a rectangle 180 degrees or less to map it back on top of itself. Okay, so I've got all of these duplicated right here. So if I start turning this, okay, no, there's 90. That's not the same. No, right here. I can spin it a full half a turn, okay, and that will take me back to looking the same. So my order of symmetry is 2. So my angle of symmetry is going to be 360 divided by 2, which is 180 degrees. Okay? If we look at the next one, I have an isosceles trapezoid. So I'm going to take this one and I'm going to start turning. No. There's 180. All right. I spun 0 to 180 without having it match up. So that being said, there is no rotational symmetry with an isosceles trapezoid. So that means there's no order and there's no degree. All right, let's take a look at a parallelogram. All right, as I start spinning a parallelogram, nope. There's the 90, and we keep coming around to the 180. Okay, so just like a rectangle, my order is going to be 2. And my degree of rotation is 360 divided by 2, which is 180 degrees. Again, just like the rectangle. All right, when we look at the hexagon, if I start turning, no, yes. Now, notice I stopped about here. I did not get a full 90 degrees. A full 90 degrees actually makes it look different. That's a 90 degree. So a hexagon does not have a one of our normal rotations, like the 90, 180, 270, whatever. So if I look here, okay, my order is, again, the number of times it's going to take me from picking one point to coming all the way back around that point. So 1, 2, 3, 4, 5 to 6. So my order is 6, which makes my degree of rotation 360 divided by 6, which is 60 degrees. All right, again, if you have any questions on that, make sure you write it down now. So go ahead again, let's pause your video. Do this problem on your own, and we'll come back in a minute to check your answers. All right, go ahead and check your answers. So for part A, the question is it possible for a figure to have rotational symmetry but not line symmetry? Yes, if we look at the examples that we did and we look at a parallelogram had rotational symmetry, but it did not have line symmetry. And then for part B, we have a student claims that a figure has rotational symmetry and that the angle of rotation is 360. So with a 360 degree rotation, everything works when we turn it 360. So this figure would actually have no rotational symmetry if it needs to be spun the whole 360. Either that or the student got the angle wrong. If the figure does have rotational symmetry, then they did not do the smallest possible angle. All right, so if you have questions on that, write it down and we will see you in class. Have a wonderful day.